Okay, 8.1, exploring the logarithmic function. So we're going to recall algebraically solving for the inverse. So there are 4 steps when we solve for the inverse. Okay, if we have a function written in f at x notation, what we're going to first do is just sub in a y for that. Okay, we're going to change the notation. Then what we're going to do is we're going to exchange the x and the y. Okay, we're going to rearrange and solve for our new y, right? So new y, and then we're basically done. And all we do is we sub back in the f inverse at x notation. Okay, so this is just a recall, because when we're dealing with the logarithmic function, it's actually the inverse of the exponential function. So let's recall the exponential function. And this is going to be a focus in this unit as well. Okay, so we have f at x equals a b to the x. Okay, a is the initial amount, and b is the base. Okay, and that's the percentage or the proportion that your initial amount is going to increase by or decrease by. Okay, so in example 1, what we're going to do is we're going to graph the function f at x equals x, 2 to the x. Okay, this is an exponential function because, as you can see, our x is in the exponent, right? Exponent function. Okay, and its inverse, we're then going to graph its inverse by creating a table of values for each. Okay. Then we have a domain and range box below, and then we're going to state the domain and range. So for each of these, what we're going to do is we're going to sub in every x into this exponent. So we would do 2 to the negative 3. And we're going to keep it as a fraction because I'm going to show you a pattern. I'm going to get 1 over 8. 2 to the negative 2, I get 1 over 4. 2 to the negative 1, I get 1 over 2. Anything to the 0 is just 1. Okay, 2 to the 1 is 2, 2 squared is 4, and 2 cubed is 8. And the horizontal asymptote for any exponential graph starts at y equals 0. That only changes if the graph has a vertical shift up or down. Okay, so that's our horizontal asymptote. And we are going to graph 0, 1, 1, 2, 3, 8. 6, 7, 8. And then this is going to be a half, a quarter, and an eighth. Okay, we're going to get closer and closer to that horizontal asymptote, but never touch it. Okay, now f inverse at x. So what we want to do is, we know that the f inverse, when we're dealing with ordered pairs, we can simply exchange the x and the y. So instead of us having the point negative 3 comma 1 over 8, we're going to have 1 over 8 comma negative 3. Instead of having negative 2 comma 1 quarter, we're going to have 1 quarter comma negative 2. Instead of having negative 1 comma a half negative 1, and then keep going down. 0, 1 turns into 1, 0, 1, 2 turns into 2, 1, 2, 4, 4, 2, 3, 8, 8, 3. Okay, so we're exchanging the x and the y all the way down the columns. And now, instead of having a horizontal asymptote, we're actually going to have a vertical asymptote at x equals 0. And we can go ahead and graph. So an eighth is going to be at negative 3, a quarter is negative 2, a half is negative 1, 1 and 0, 2 and 1, 4 and 2, and I didn't make this so that the 8 fits, so this is just f inverse of x. Okay, and as a recall, just to remind everyone, The inverse is the reflection in the x equals y line. Okay, so let's talk about the domain and range. So for f at x, that's this blue graph right here. F at x, the domain is xer. It's going to hit every single number going to the left and the right. Okay, just like any other exponential function. Now the range is going to be yer such that y is greater than 0. Okay, the other way you can do this is 0 to infinity. Okay, you can choose either method here to write. It does not include 0 because there's a horizontal asymptote at 0. Okay, for xer, you could also put negative infinity to infinity. Right, that's another way of writing that. Now, let's take a look at the inverse. Okay, inverse function. Our domain is from 0 to infinity, but it never touches 0 because there's the vertical asymptote. So xer such that x is greater than 0. The other way to write it is 0 to infinity. Okay, in regards to the range, yer. We can see that this goes down forever, it eventually goes up forever, so just yer. Okay, the other way of writing that is negative infinity to infinity. Now, I want to point something out. We learned back in grade 11, but it's back. Because we exchanged the x's for the y's, we actually also exchanged the domain for the range, which is very logical. So if you can see, the domain of the original is now the range of the inverse. Xer, yer. Now the domain of the inverse is the range of the original, or vice versa, right? Y is greater than 0, x is greater than 0. And that makes sense because we're literally just switching the x and the y. We're substituting them out for each other. Okay, let's talk about the logarithmic function and the exponential function. So the logarithmic function is the inverse of the exponential function. So if we have y equals log base ax, and by the way, this a cannot equal 0. Okay, we're also going to have f at x equals a to the x. Okay, a is a base, a cannot equal 0. A actually can't even equal 1. So you want to add that in there. Okay, because if we have 1 times 1 times 1, x number of times is actually going to be a horizontal line at 1. It doesn't turn out to be exponential. Okay, we also can't have a base of 1 because of this reason. Okay, so converting from logarithmic form to exponential form. An equivalent form of the logarithmic form of this is usually written as this. So this is how we toggle between logarithmic and exponential form, and we're going to see this a lot in our questions. Okay, the expression log base ax means, and a lot of times they don't write this as like y equals. So it's a little confusing because now you have to introduce that y. But what this means is the exponent that must be applied to the base of a to get to the value of x. That's what that means. Okay, so as an example, log base 2, 8. So what exponent do we need to apply to the 2 in order to yield the answer of 8? Well, it'd be 3. It'd be 2 to the 3 equals 8. Okay, so since y equals log base ax and x equals a to the y are equivalent, a logarithm is an exponent. That's crazy. So the shape of the logarithmic function depends on the value of the base. Okay, so remember this. C is like log base a. Well, a is also the base. So either one, we're talking a is the base. That's how I remember it. So a to the y equals x. A to what exponent equals x. So when a is greater than 1, the exponential function is an increasing function. So that means it's going up to the right. That means that the logarithmic function is also increasing. Okay, so it's going up to the right. So increasing exponential is increasing logarithmic. Now, if a is, I call this a fraction, but remember a fraction or a decimal could also be greater than 1. Like for example, like 5 over 2 is actually 2.5, which would be increasing. But if we have like a fraction like between 0 and 1, the exponential function is now decreasing. Okay, so it starts up and then it decreases reading to the right. The logarithmic function is also decreasing. Okay, and let's compare some of the properties and characteristics of an exponential function versus a logarithmic function. So, exponential function has a horizontal asymptote, y equals 0, whereas logarithmic function has a vertical asymptote, which is like the y-axis, x equals 0. Okay, both of them have an intercept of 1. Exponential function has that y-intercept of 1 right here. Logarithmic function has an x-intercept of 1. That just totally makes sense because a y-intercept of 1 is 0, 1, and when we find the inverse, it'd be 1, 0. So that makes sense. Okay? And also remember, these are inverses, so the domain of the original is now the range of the inverse, and the range of the original is now the domain of the inverse. Okay, now let's talk about algebraically representing logarithmic versus exponential. So express each of the following in exponential form. Okay, so y equals log base 2 to the x. If we remember, just like a little aside, okay, y equals log base a of x is the same thing as saying a to the y equals x. Okay, same thing. So coming over here, 2 to the y equals x. 2 to the y equals x. Like this is saying again, 2 to what exponent gives us x. And that's it. That's all this question is asking for. Just rewrite in exponential form. Done. So y equals log base 5 to the x is going to say 5 to what exponent gives us x. So 5 to the y equals x. And then done. We just toggled between logarithmic form to exponential form, depending on where your comfort lies to deal with the laws of logarithms, the laws of exponential. So express each of the following in logarithmic form. So again, y equals log base ax, same thing as writing a to the y equals x. So in this case, we have y equals 4 to the x. So you know what we have y equals? It's the exact same thing. If we have y equals some number a to the x, this is going to be the exact same thing as saying x equals log base ay, right? The only thing that's changing here is that the x and y are just written in different positions. No big deal. So to write this as logarithmic, so we're saying 4 to what exponent equals y? So we're saying log base 4 to what exponent equals x? 4 to what exponent equals y? Okay, and for this one, y equals 10 to the x. I'm going to say x equals log base 10, and that 10 is the base in the exponential function. The 10 is also the base in the logarithmic function. So it's like 10 to the y equals x. So 10 to what exponent x is going to yield us y? Okay, example 4. Evaluate each of the following. So this is actually evaluate. By first converting into exponential form, step 1, by letting each expression equal x. Okay, so here's the thing. In your textbook, it's like the most bizarre thing ever, but you're going to get questions where it's log base 2 to the 4, and all of a sudden, like in the solution, you have to convert to exponential form. So you're converting it to like 2 to the x equals 4, but you're kind of saying like, where does the x come from? So you can just go ahead and assume that all of these equal x, and that's your variable. Okay, so 2 to what exponent gives us 4? Well, we can go back to our grade 11 approach of same basis. So 2 to the x is going to equal, well, what can we sub in for 4? We can sub in 2 squared. Therefore, x equals 2. And if we go back here, it actually makes sense. 2 squared equals 4, right? 2 to what exponent? Okay. Next one. 5 to what exponent equals 125? So first, exponential form. 5 to the x equals 125. Okay. Now, we're at 5 to the x equals, well, what's 125 written as a base of 5? Well, it's going to be 5 cubed. Okay, drop the 5s, we get x equals 3. Okay, and that's how we're evaluating. Okay, last one. Log base 3 to the 81 equals x. So 3 to what exponent equals 81? Okay, so if we have 3 times 3 is 9, times 3 is 27, times 3 is 81. So this is 3 to the exponent 4. So in this case, x equals 4. Okay, so we're going to equate log base 2 to the 1/8 equals x. So our question is 2 to the x equals 1 over 8. 2 to what exponent equals 1 over 8? Well, as a review of exponent laws, if we have some exponent, let's call it m, some base m to the negative exponent, so negative n, what ends up happening is this number m has to be flipped. It's now going to be flipped to 1 over m. And now instead of writing the exponent as negative, we can write it as positive. So we know when we have 2 to the x, we're going to have some negative exponent if our answer is a 1 over 8. So if you think about the number 8, 2 to the 3 would give us 8. But our number is not 8, it's 1 over 8. So we put a negative sign on it. And our x equals negative 3. Okay, log base 3 of 3 equals x. So in this case, 3 to the x equals 3. Okay, well, this is kind of already done for us. We have the same basis. Please don't put a 0 here. This is 1. 3 is as well considered 3 to the 1, so x equals 1. And by the way, this right here is going to come back in a future unit. And we're going to have log base, for example, m to the m. This is just going to cancel to 1. However, this is the reasoning. Okay, and the next one, log base 2 to the 0 equals x. So 2 to the exponent x equals 0. Okay, 2 to any exponent is never going to yield a 0. This is going to be inadmissible. Okay, the reason why this is inadmissible is because if we consider this, and we consider the logarithmic function, when is the logarithmic function going to equal 0? Which is right here. Well, it's not, right? Because it's not in the domain. So not in the domain. Because there's a vertical asymptote at x equals 0.